Good afternoon. Welcome to week 6 of the course Coherence and Quantum Entanglement offered by NPTEL. So this is week 6, that is we are halfway through. This is 12-week long course and we will begin today's session with some problems from the previous week. We solved a few questions last week and then a few questions were remaining, so we will complete that today. Before we move on to a new set of questions. So this question is related to the previous question. Let me go over the previous question first. So in this question, we were given the angular correlation function for the Gaussian shell model pump field. And then we had to show that the cross spectral density at z equal to 0 took this particular form. And further, we had to find out the cross spectral density in the far field, that is for very large z. So for the Gaussian shell model with this angular correlation function, we found out the cross spectral density function both at z equal to 0 and for very large z. And just to revise, so this is how you find out cross spectral density from the angular correlation function. This is for z equal to 0. Then we did a lot of manipulations to solve the integral, and this Gaussian integral is very important. And then this is how you find out the cross spectral density at a particular z. Again, using some manipulations to solve the integral, as well as some approximations for far field. So for far field, z is very large. We made use of certain approximations. And after all of those manipulations and approximations, this is the expression that we get for cross spectral density function at very large z. Now the terms in this expression is that sigma mu is the transverse coherence width. And sigma s is the size of the beam. And sigma mu is a function of z we saw. Let me go back to that place. Yeah, so this is the expression sigma mu as it varies with z. Similarly, sigma s also varies with z as shown over here. So the question is, in the previous problem, we found out that the transverse coherence length of the field depends on z. In this problem, find an angular correlation function of finite transverse spectral width delta q such that the coherence length of the resultant field is finite but does not depend on the propagation distance z. So think about it. If you want, I'll just scroll over to this question so that you can recapitulate. Okay, so let us now start solving the question. Now, let me go back to this expression and copy it. So this is the expression that we will be making use of. This is cross-spectral density function at a given z when we know the angular correlation function. So w rho 1 rho 2 z is integral of a, which is the angular correlation function, times this particular exponential, which is involving q dot rho terms, and then another exponential which involves the z term, and this integral is over d squared q1 d squared q2. Now let us look at some extreme cases, some special extreme cases. For the angular correlation function A. So first extreme case would be if we assume perfect correlation. So this is the expression for A when there is perfect correlation. And the field is given as follows. And so finally the cross-spectral density can also be written as follows. As the correlation between u star rho 1 z and u rho 2 z. So this, if we plug in this particular expression, will become the following. Now this we can see will clearly be a function of z. Why? This is because of this presence of this z exponential over here, which is not getting cancelled out or integrated out in any possible manner. So it will exist even in the final integral in some form. So because the integral is over q1 and q2, so q1 and q2 will get integrated out, but z will still remain. So this will be a function of z. So this is in this it will not be possible for coherence length to be independent of z, because w depends on z, therefore the coherence length will also be dependent on z. Now let us consider the other extreme. We considered perfect correlation, now let us look at no correlation. In this case, the angular correlation function will be as follows. It will involve a delta function. Now if I write my cross spectral density function, now plugging in the expression for A, now because of this delta function and integral over q1 q2, so we get is q1 equals q2. So this will become so because of this integral, let me highlight. So because we have over here this delta function and then we are integrating over d squared q2, so that will give us q1 equals q2. So because of q1 equals q2, this particular term will then vanish. As a result, this entire exponential will become equals 1. So we will get rid of the z dependent term. So this is independent of z. So because W is independent of Z, therefore the transverse coherence length, which is essentially the width of the W function, the cross spectral density function, because of that, this coherence length, transverse coherence length, will also be independent of Z. And this is what we wanted. So this is our desired condition. The question had asked us to find out a situation, find a particular angular correlation function for which the transverse coherence length is independent of Z, and we have found out exactly that. For this particular expression of of angular correlation function, the transverse coherence length does not depend on Z. Because this integral itself is independent of Z. Okay, so now let us move forward to the next question. Consider the situation as shown in the figure below. This is the figure. In this figure, we have a stochastic field V phi which falls onto an aperture in the form of a double angular slit. So this is a double angular slit, one slit at angle phi 1, another slit at angle phi 2. And the expression for V phi is given. Then we have to consider that these angular slits are infinitesimally narrow, so they do not have any width. That is, take the aperture function to be the following, which is sum of two delta functions. We have a detector dA. So the detector dA measures the intensity in a mode with orbital angular momentum OM index L. We have to define an expression for intensity at the detector as a function of the OM index L, and part B says find out the explicit expression for the intensity at the detector as a function of the OM index L when we have this particular condition that CL equals 1 for L equals L naught and CL is equal to 0 otherwise. So take some time to read this question again and then we will solve. Okay, let us now solve. So we are given V phi as following. Which falls on the double slit aperture, and we are also given this correlation between the alpha function and the aperture function is sum of two delta functions. Let us look at problem A. Now, because we are given this particular expression for the correlation between alpha, this means that the field is stationary. The field is stationary and there is no correlation between different OAM modes. So let us now look at the field at the detector. This is the field at the detector, which is contributions from angular slit 1 and angular slit 2. So this intensity then turns out as contributions from the first slit plus the contribution from the second slit and then cross terms. So now let us look at the cross terms. So this term is the cross spectral density function. So the summation, both the summations run from negative infinity to infinity. Now this we are already given is c times delta function. This over here, so this is CL1 delta L1 L2. So one summation will go away because of this delta function when we sum over this delta function and sum over L2. So let us perform the L2 summation. We will perform the L2 summation. This will leave us with L1 summation. And because of this delta function, L1 equals L2. This is what we get. So delta phi is nothing but phi 2 minus phi 1. Similarly, for the other cross term, it is just the complex conjugate. And also let us look at the intensity contributions from the individual slits. So both the summations are from negative infinity to plus infinity. Again we will perform summation over L2, and this delta function is there. This will give us L1 equals L2. So when L1 equals L2, this term will vanish away, and so this exponential will become equal to 1. And this is also the same as the intensity contribution from the other slit. Now putting it all together, and this summation over CL will be equal to 1. Or sorry, so this will be in the next question. We will see by plugging in the values of CL. So this is for part A. We found out the intensity at the detector, which involves the terms CL and delta phi. In part B, we are given that CL equals 1 for L equals L naught and it is equal to 0 otherwise. So when we plug in these values in this above expression, we get the following for the intensity at the detector. So this will equal 1. This summation will also pick out the value only at L equals L naught. Same for this summation, it picks out the value at L equals L naught. Let us look at these terms K1 star K2. So plugging it back into the expression for intensity. So this is the final expression for the intensity at the detector given these conditions. So this completes the problem involving the double angular slit and the field at the detector as a result of this interference. And with this we have also completed the problem set that we had started in the last week. So we had started with this particular week 5 problem set, but we could not complete it. So right now we have completed it. Now we will move to the current week's problem set. Just to recapitulate, in the last week we solved problems involving this Wolf equation, then propagation for the cross spectral density function. Further, we saw how to find out the cross spectral density function given the angular correlation function. Both had z equal to 0 and for far field z. And then we had to solve these questions which we solved today, which involved finding a particular condition in which the transverse coherence length would be independent of z. And finally, the angular double slit interference and the intensity at the detector as a function of the orbital angular momentum index L. Now we can proceed to the new problem set. Okay, so now we move in to the next set of problems. This is the problem set for week 6. Let us start with the first problem. What is the difference between a pure state and a mixed state? Part B. What is the difference between a coherent mode and an incoherent field? Can a coherent mode be a pure state? Part C. What is coherent mode representation of a field and why does one need it? Is there any relation between the number of modes in the coherent mode representation of a field and the degree of coherence? Part D. How many modes are there in the coherent mode representation of a field that is completely coherent? Give an example of such a field. Part E. How many modes are there in the coherent mode representation of a field that is completely incoherent? Give an example of such a field. Okay, so take about a few minutes to read and then I will answer it. Sorry. Okay, so let us now discuss the answer. This is part A. This is a more of a descriptive type question. There are no equations to basically work with. So pure states are states which are represented by a single wave function or which could be a linear superposition of eigen states. And mixed states are statistical mixtures and they cannot be written down as a wave function. And representation of mixed states can only be through density matrices. And eigenvalues for density matrices is for pure states is either 0 or 1. In our case of optics, a pure state would be fully coherent state and mixed state is partially coherent. So, as described in part A, coherent state is a pure state, whereas an incoherent state is a mixed state. In incoherent field, the correlation between different field points is not perfect. Coherent mode representation decomposes a partially coherent mode as a superposition of coherent modes. The propagation of coherent modes are easier to study. So that's why we would want to decompose a partially coherent mode as a superposition of coherent modes and individually study the propagation and then add them together. A coherent mode would have only a single mode in the representation, whereas for incoherent modes, we would require infinite coherent modes in the representation. Thus, the degree of coherence is inversely related to the number of modes in the representations. So as described in the previous part, a coherent mode would require just a single mode in the coherent mode representation. An example is a monochromatic plane wave. And as described in this part C over here, an incoherent mode would require infinite modes in the coherent mode representation. An example for such would be sunlight. So this was about pure and mixed states and coherent and incoherent mode and coherent mode representation, and how to represent coherent mode and incoherent modes. Sorry. So moving on to the next question. Show that a general polarization matrix J can be uniquely expressed as a sum of two matrices, one of which is completely polarized and the other one is completely unpolarized. So matrix for unpolarized light or field this is the matrix for polarized, and for this the determinant is 0, and B and C are greater than equal to 0. That means trace is positive. Now, the general polarization matrix is given as J, and this can be written as the sum of polarized and unpolarized matrices. So the general matrix is sum of polarized part plus sum of unpolarized part with a constant. Now we need to show that this decomposition is unique. Now we can compare the LHS and RHS. So trace is sum of the diagonal elements. And this is the determinant. So the determinant condition that we wrote over here for this polarized part, let us look at that now. Now let us look at the roots of the above equation. Now first let us consider the first root, which is a1. Now trace J is jxx plus jyy, and determinant is this over here. We'll make use of that. Now similarly we can look at the other root. Now as we can clearly see, both b1 and c1 are less than 0, because there is this additional term over here inside the square root, and had it not been there, then this difference jxx minus jyy minus square root of the first term, that would give me 0. But having this additional term means this is larger than just this first term. As a result, this whole term becomes negative. Same with c1 also. So from this we get both b1 and c1 are less than 0, which violates the initial condition. So this violates the initial condition that we had over here in equation 2. So because this violates this condition, this means that A1 is invalid. Now let us look at the other root. And this is also this will be positive now because of this plus sign. So finally we conclude that A1 is invalid and the only unique root is A2. So thus we see that the decomposition is unique. So we this is how we prove that the decomposition is unique, by finding out the value of this A, which is unique. So Okay, so next question. A polarization matrix can be expanded as a linear combination of identity matrix and three Pauli matrices. And this is the expression how it is written. And this Si are called Stokes parameters and sigma I are the Pauli matrices, and all the Pauli matrices are listed down here. The question is part A. First of all, show that for a general polarization density matrix, determinant of J is greater than equal to 0. And then show that, this is part B, show that S0 squared is greater than equal to S1 squared plus S2 squared plus S3 squared. And part C is express the degree of polarization P in terms of the Stokes parameters. Okay, so take about a few minutes to read the question and then we will solve. Okay, so let us now solve. So this is the polarization matrix J. I have expanded it out over here, and then using these Pauli matrices, S0, S1, S2, S3 are constants, and plugging in these Pauli matrices in this expression over here, we get this matrix in equation 1. And then the determinant is as follows. So let us expand. Now the general polarization matrix, as we saw earlier, can also be written as follows. So this is coming from the previous question. So this, now we can write the determinant. Just manipulating and simplifying. Now this is because the determinant for the pure part BC, my this pure part over here, this polarized part, the determinant for this is 0. We saw this in the previous question. We can see that. So here we wrote this polarization matrix, then wrote it as the sum of polarized and unpolarized parts. And also from this equation we know that the determinant for the polarized matrix is 0. Now this is positive because A, B and C all are positive. That's because here we know that we saw previously B and C are positive, A is also positive. Okay, now we can move to part B. We'll make of this equation 2 in part A. And also the determinant is positive. Let me call this part equation 3. So that means this is greater than equal to 0 because this was determinant of J from equation 2 of part A. So this implies we can rearrange Now we can move to part C. And this is the degree of polarization. So from here, so this is determinant, and let us now find the trace. So this is by plugging in the expressions for determinant and trace in this degree of polarization. And then simplifying, So this completes this question. Now we can move on. Just take about a minute to recapitulate. Okay, now moving on. Consider two separate and uncorrelated lasers. The field from the first laser is polarized along the x direction, whereas the field from the other one is polarized along theta direction. The two laser fields are mixed at a beam splitter in equal proportion. Part A. What is the degree of polarization of the resultant field? B. What is the degree of polarization when theta equals 0? C. What is the degree of polarization when theta equals pi by 2? So take about a minute to read. Okay. Fine. Let us start. So this is x direction, y direction. And theta cap unit vector in theta direction. Now let's look at the beam splitter. So this is the beam splitter. We have laser 1 as the input, field E1, then laser 2 at the other input, which is field 2, and then at the output port the combination will give the net electric field, and this 1 over root 2 factor is coming from equal proportion of splitting. So assuming this is a 50-50 beam splitter, so now since we have all this framework ready, the coordinate system and what happens at the beam splitter, let us start solving. So first laser along x direction, second laser along theta direction, and plugging in this expression for theta. Now after the beam splitter, let us write down what is the resultant field. So the net electric field is the sum of these field contributions from laser 1 and laser 2. And then let us split in the x and y directions. Write it in the x and y components. So this is x component and y component. Now let us write the polarization matrix. This is the polarization matrix. So this is ex component, and this is the y component. Now let us expand it. Now for normalized fields, this is one, same for E2. So wait, let me E1 star E2T plus E. Okay, wait. I have made a mistake somewhere. This should be E2 star E1T. Yeah, so E2 star E1T. Now we can further look at this E1 star E2 terms. So for the lasers, the amplitude of the field can be taken to be independent of time. So we can replace E1T with just E1 and E2T with E2. Okay, sorry, I think I'm already over time. We'll just quickly finish this, or maybe we can continue next time. Okay, so I think we are still at part A and we have parts B and C also to do. So maybe we will continue from the next time. Next time I will repeat this question once again and then we will move ahead. Okay, so thank you and see you next week.